comes in many forms, and one of the best known is the diamond, the hardest of all natural materials and among the most beautiful. A unique element. It can bond with itself and with other elements. A diamond is made up of pure carbon and sometimes contains other materials that are called integrals. The carbon atoms in a diamond are arranged in a crystal structure. Each carbon atom is bonded to 4 other carbon atoms. This arrangement makes diamonds both strong and stable. Diamonds do not easily react with other chemicals. Diamonds form about 160 kilometers underground. There, pressure 5,000 times greater than surface pressure, and temperatures over 1,000 degrees Celsius, nearly hot enough to melt iron, cause carbon atoms to form diamond crystals. The beauty and popularity of diamonds make them one of the most well-known forms of pure carbon. But actually, most carbon comes in this form: graphite. Graphite is a strong material that is often combined with other materials to reinforce everything from golf clubs to fighter planes. In graphite, a carbon atom bonds to 3 nearby atoms to form flat layers. Each graphite layer is incredibly strong and stable, although only 1 atom thick. It takes millions of these layers just to form the tip of a sharpened pencil, which is actually made of graphite mixed with clay. Every time you write with a pencil, you're rubbing off layers of carbon in graphite. Although the bonds between atoms within a graphite layer are strong, the forces between atoms in different layers are weak. So because the layers can slip past each other, graphite is soft.
Hydrogen bonding in a solution, we're going to use some cobalt chloride and add that to this graduated cylinder. Then we'll add acetone slowly down the side of the graduated cylinder. The acetone hydrogen bond with the cobalt chloride solution. The acetone is less dense. The aqueous cobalt chloride solution, the blue layer will appear on top. The reaction seen is an equilibrium reaction. The hexahydrate cobalt-2 ion reacts with 4 moles of chloride ion in an equilibrium relation to 1 mole of the tetrachlorocobaltate ion and 6 water molecules, or 6 moles of water. Action, the acetone combined with the water bonding, effectively lowering the concentration of the water available to the equilibrium. As a result of this decreased concentration, shift in the equilibrium from the pink to the blue in the upper acetone layer. A demonstration perhaps that you've already seen is when a glass is completely filled with water. Then a cardboard is placed over the glass. It's inverted, and then the hand supporting the cardboard is removed. Atmospheric pressure causes the card to stay in place. This demonstration can actually mislead you regarding the understanding of the next demonstration. Let's add a little food coloring to this water so that it's more visible. Now let's pour that water into a mason jar with a wire screen lid in place of the normal cap. And so the water enters the jar. Once again, we'll fill it to overflowing. We'll place a card on the screen and turn it upside down. But this time, instead of removing my hand, we'll remove the card. The question is, why doesn't the water come out through the screen? Surface tension is the answer to that question. The surface tension of the water around the small holes in the screen. If we tip the jar just slightly, we're able to cause the water to come out through the screen.